So, enabling virtual product validation. That's the line I'm starting since 6 years, and I try to bring every time a little bit of a different aspect into the spotlight in order to present to you the challenges and solutions that we have in that ecosystem, in that space that we are operating in. Today, it's about creating a proof of validation by empowering an open and distributed data ecosystem. And that context is given by a research project, which is GaiaX. How do we start this? I would say I like to look sometimes at headlines. And some of these headlines here are from 2020. But if you see that there was a review of the perceived safety of certain elements, and Tesla got a moderate and BMW a good grade. So I don't want to gloat over the fact, because there apparently is a large community of people that post videos how technology saved their lives. So I was thinking, how can it happen that something then gets this grade moderate, and what is behind that? So if you look into the report, you will see that there is a statement that the Tesla system named Autopilot is inappropriate as it suggests full automation. And so the promotional material is correct, but this could lead to confusion to the customers. And confusion is something that I think is accompanying us sometimes when we interact with each other, and we have to try to get rid of it. And how can that confusion also be described? It's in this case, a mismatch between the expectation and the actual specification. And it's not intentional, but often due to the ambiguity of the language that we're using. So it's about confusion and language and the exchange of information. I was having a talk in 2019. It's on YouTube if you want to search for it. It was about the release of the open simulation interface as ASAM OSI, so it became an ASAM standard at that time. And all the standardization was meant with a specific goal. You wanted to have the integratability of models. You want to exchange maps and scenarios, and you want to have a modular framework and transparency in the architecture. And all of that you do to have a cost down. And if we look back at the time when that was presented, and now, we will see that there came a whole ecosystem that is now consistent of ontologies, OpenDRIVE for the maps, OpenScenario for the dynamic part, OpenCRG for the surface description. We have a project that just started about ODDE. So actually there's a lot of traction there, and this traction can also be seen by the memberships the members that came to ASAM. These are already old numbers, so we have 400 members now in ASAM, companies, which I think we had 200 members since that came to ASAM since we opened up the new section of ASAM OpenX, the simulation standards. And that's a fantastic success. And it just says that building a community of people, bringing people together at a table and let them talk about their problems and let them figure out ways on how to understand each other, how to create languages where they can exchange information and the people know what it means, is something extremely important. And that, at that conference in 2019, I stopped with a view into the future. And I will repeat the problem statement that I've seen there. So, because, I mean, we could say now, oh, we have ASAM, we have all the standards, the problem is solved, simulation is ready. But there are still problems left, and I want to try to point out the challenges that we have here. And it normally, at least in my case, starts with the simulation. There are different simulation tools, different vendors. Even in companies itself, we build different proprietary tools. And all of these tools, they incorporate simulation data. So we have maps, we have 3D models and geometries, we have material data that is attached to these geometries, and we have the dynamics of the scenario. And those are just naming a few things that all flow into the simulation and need to be integrated. And what you can see here is just a little bit of name dropping of a few random companies. We span up an ecosystem of companies that is very broad and deep. So we have a very complex supply chain actually in this simulation area. And it doesn't stop with the simulation tool, because there's obviously a user somewhere that wants to use it. So it's, for example, the tier 1 that has to provide a camera to BMW. And that camera comes along with a sensor model. Maybe it is using ASAM OSI, right? And at the tier 1, you have a simulation. At the OEM, you have a simulation. And we need to integrate those models and also the models from others, and then put our functionality on top. So we said it is enabled by standards, but the question is also, why are we doing this? We're doing this to improve our development process, but the end goal, the virtual product validation, is somehow that we want to prove something to someone. Maybe we want to use it to show it to someone. Maybe to support a virtually enhanced homologation process, that somebody has a strong trust in that simulation. And what you should see here is that complex flow of data and information from the top left to the bottom left. And it's basically an ecosystem that it consists of different databases. Somebody gives it you the data with a USB stick. Somebody else has a download link, and it is all a bit Wild West. So at the time, I came up with a vision of a distributed ecosystem. We call it the invited ecosystem, environment for virtual test drive. And we structured a research cluster in a German industry club, which is the Automotive Simulation Solution Center for Simulation. So it's very similar to ASAM, which is also an industry club, where we come together, and where we try to solve this issue of this ecosystem and that we see there. And I mean, to just repeat what this is for, it's creating a virtual proof of validation. And we basically need this because we have blurred life cycles. They are getting shorter, and they overlap, and we have stricter requirements with more complex functions. And we have a growing proportion of software and an increased update frequency and growing dependencies, and we even want to update when cars are already in the field. And the conventional methods of validation, the physical testing, they do not suffice, and they cannot handle the amount of required testing. Well, that's obviously that we need to complement it with the simulation parts. And we want to have the simulation parts it should have the same relevance as the physical testing if somebody needs to believe that we're doing it right, what we're developing. So what are a few of the challenges? For example, the question of what makes a map HD, or what makes a scenario relevant. So we are attaching certain attributes to something like a map, but actually what is the content of an HD map, right? I mean, we have OpenDRIVE, we can describe a map with that, but what does it make HD? And if you walk around and see the different booths, people say, I'm giving you the relevant scenarios. So why are they relevant? And what is your methodology on how to derive that attribute? And actually, do we have the same understanding of the standard that we have defined? I mean, there's no claim of perfection here. We know that there may be lacking definitions, and we have to figure them out and do iterations and improve them. And do the involved tools that we have, and we have seen in the tool chain, actually support the feature sets of the standard? Every standard has different features, right? And if somebody says, I am supporting open scenario, I'm mostly asking what features of open scenario. And then it goes into a little bit of a cumbersome discussion. Because it's also hard to, we lack the examples here. And what are the general quality measures that have been taken to assure and make it visible all those problems and challenges? And how are these quality requirements also connected to a use case? So, I mean, we have to have a reason why we want to have a feature in. So a lot of challenges, and I want to give you some examples in what things can tackle them. So there is not the golden goose, not the one solution. It's a basket of a lot of solutions that we have to apply and understand. First of all, an example of deriving requirements from a use case. We have the ALKS regulation UN R157, and it defines the automated lane keeping system, so what kind of feature is it, and what is required for it to be allowed on the street. So it's a document written in English, and it has an annex. And the annex is not the binding part, but the written part. And the problem of that is that somebody needs to read it, understand it, and derive from it what needs to be done. And normally those regulations, and we had it in the panel yesterday, are a little bit high level and by intention vague, because it needs to be interpreted with a technical service together. It's also because those people can hardly look into the future, and we try to figure out a way on how to derive the proper testing methods along the way. So what is it what we need? We have, first of all, the regulation, the document itself, and it needs interpretation, and interpretation by a community. A community can be company internal, but it can also be broader. It can be a community of people in a research project, for example. So we read it together, we talk about it, and we try to figure out what we need. And then we say, okay, there's a set of scenarios that I have to test there. So we have to pick a standard to implement those scenarios in order for somebody else to read it, apply it, and understand it. And then there is the question, did I do it right? So I have to go into the CI pipeline here. You see the link on the bottom. It's open source on GitHub. And if you go into the pipeline, you will see that there are several checks that try to say, here's a green light, you did it right. And there's not the one check that gives you certainty, but it's best to have multiple checks, because if I have multiple green light, I basically create kind of a network of trust from different companies. And I want to showcase that it is important to have multiple sources that confirm the correctness of something. So what is the next source? The next source might be the execution of that in a simulator. So I love to pick, for example, ES Mini, which is a great open source simulator that Emil Knabe from Volvo built, just to understand open scenario. So there's another one, OpenPath from BMW, and so I'm picking those simulators and I'm executing the scenarios there. And what did I find? Some are not executing, but people claimed we support open scenario. And I said, look, there's one feature, it's not supported. So now they realize, now they fix it. So we need those examples in open source, accessible, describe it together, tie it to use case, to have a reason why we want to do it. And then we discover a lot of issues. Example number one. Example number two, there's, by Marius Dupuy, he's now the managing director of ASAM, an expert for simulation since many years, founder of Virus VTD, and he has a website which is simcert.org. And it's very interesting to pass through the different policies on where he tries to rate a simulator, the quality of a simulation. And one part of a quality of a simulation, and you see on the right side, it's a little bit like an Amazon-style star rating. There is standard compliance as one of the criteria. And you will see ES Mini has great standard compliance. I can confirm that. I've tried it. So there's the second example of expert opinion that can give an idea on how a simulator is good or not, or what parts of it. So that could be another element in our proof of validation, that we provide proper data tied to use cases. We have validated that the data is correct and has a standard. We use proper simulators that are rated by objective criteria, and that can say something like, this is very standard compliant. So how can a simulator become standard compliant? They need to implement them. And the same way they need examples, for example, for understanding open scenario. The third example might be that if we talk and go back to the open simulation interface for the integration of sensor models, you would also need examples to integrate sensor models. So what's the next step? In the same industry club, Automotive Solution Center for Simulation, we have established something that's called the Open Model and Simulation Library. So it is something very simple that is basically a GitHub workflow, written down governance model. You need a maintainer, you need to decide on the templates that you're using, very simple rules that allow you a lightweight governance, which then gives you the compliance as a large company to contribute and talk with others, and gives you the possibility to bring an element into a community of interested people that try to contribute together. In this case, for sensor models. And the first example that we have taken in are sensor models that were developed in the context of a research project set level. And I'm taking now from that ending research project, but normally when a research project ends, everything dies with it. Nobody knows what has been done. Somebody has it in a USB stick in his, I don't know, drawer. And some things have meaning for other projects. We want to build up on it. So now we can transfer those models into a community, put it open source, define the criteria of quality that we want to have there, in order for a simulation tool vendor to grab it and test his integration. There's the idea of extending this with additional small frameworks like an integration test framework for sensor models to evaluate their correctness. And so you build up with those little pieces to generate understanding. Sorry. We have another set of challenges in that ecosystem. And those challenges are, if I want to prove something with it, I need an immutable documentation that has acceptance, so somebody believes that this traceable proof that I've given them is correct. I need kind of transparency if I want to enable, I don't know, something like data markets that solves the digital rights management, for example. Everybody's scared that somebody can steal something from me. And we need to define common usage policies and licensing models for understanding what I'm allowed to do with the element that I'm taking from someone. And we need to kind of automate this process of acquiring this license for a certain simulation tool. And then the idea is you have all those different elements and they span up like a tree, and you have certain kind of certificates that attribute the quality, where is it coming from whom, why am I allowed to use it. And I bring it together in a large tree. And if there are a lot of green lights, so can you give me a water, please? If I have a lot of green lights, then I have more trust in that simulation because I trust the different pieces in the simulation. Thanks. So in order to work on that idea, we took again that community from that industry club, from our research cluster, and we created a project And this is now GaiaX. So it's a research project funded by the German state, 20 companies, 25 million in volume. And the goal is a virtual proof of validation in the context of a use case, ALKS. And there I want to demonstrate technologies and the elements that are needed to exchange those data sets and make it traceable. And we are evaluating an interesting technology, and the technology is public blockchain. So, how can that be connected? I will show you. Quick reminder what it is. A blockchain is a data structure that groups certain data sets like transaction into immutable containers, and they are put into a chain along the time. That data set is then replicated in a peer-to-peer network and is protected by the protocol, so it cannot be manipulated. So I can trust the data set and its content. That's the part. But what is interesting about a public blockchain? The interesting part is that it's driven by an open source community. And that community is often, like it's in Linux and everywhere else, or also in ASAM, which is also a community, by extrinsic motivation and intrinsic motivation. So they do it because they think it and feel it is right. It's very hard to buy people with intrinsic motivation with a BMW purchasing process. So it is... So with a community and with a common goal, it is possible to get access to those peoples and their minds. And with that, we increase the speed of development. We have an operational infrastructure. It is maintained and secure, and we lower the cost. So what you have to look at is a software project is easily built, but a community is not. And the value of a network effect is hard to measure. And the network effect is the contribution of people. The network effect in ASAM is 400 companies with people and experts contributing to something together. It's always the same and repeating element. You have it here as well. And what kind of community am I tapping in? I'm tapping into this. NFTs, digital art. It is something that is in the news a lot. And what you see here is a piece that was actually sold at the time for, I don't know, I think it was like 15,000 euro. You can say it's a ridiculous amount. But the fact is, you have marketplaces, and those marketplaces are connected by a common technology which makes those elements traceable over all of those marketplaces. And those marketplaces have different attributes. They can be very professional, they can be community-driven, they can have special features, they can have an aggregation. So the picture I'm showing is from an aggregating marketplace. What if this picture is not a piece of art, but a sensor model? And I have connected marketplaces where some specialists has one marketplace where you have specific radar sensor models or specific camera sensor models. And I need to pick the pieces from those different marketplaces and need to keep the traceability and know where it came from. And it should all be connected through common quality measures. So what I've done is link is below, you can try it all yourself. I try to bring those two worlds together. And I will show you why it's easily done. So this piece that you've seen there is maybe a JPEG. It was before a JPEG. Now it is not a JPEG anymore, but it is a sensor model. And as we have seen before, a sensor model is defined by the open simulation interface. An interface that is using protobuffer as a data description language, is maintained in ASAM, and this model is packaged as a functional mockup unit. So it's using another standard. And the definition of this package is called OSMP, OSI Sensor Model Packaging. So it's the container of it. So the right block below is the container which describes the sensor model. This is where we stopped 2019. Now the question is, how can I describe this element further to give it to somebody, and that person needs to understand what the content is. So what did we do in the set-level research project? We defined something that's called simulation resource metadata. Something very simple. It's just a JSON file, and it describes the author, the manufacturer, the model that it is referencing to, the standards that are used, attributes and content, and how it has been checked. But you have to come to a conclusion in a community. What elements of the metadata are important for you to understand it? And that schema is derived from SSP traceability. It's a layered standard on top of system structure and parameterization. So it is system structure and parameterization allows you to define not a single FMU, but an architecture of FMUs, how they are parameterized, and so on. So, and now I'm tapping into the new world. And the new world is the blockchain world. And I'm referencing to another set of open specification. They are called TZIPs. And there, again, I have a token, a certificate describing the data set. So we have two pieces, the data and the certificate. And the certificate is living on a certain piece of infrastructure, and then I can trade policies from left to right. And we have to describe that as well, the token metadata. And then this lives on a distributed data system. In this case, it's like Dropbox, but in distributed, the interplanetary file system. And the top left is then the last element. That's the contract defining the functions to create such a certificate. Create certificate, transfer certificate, destroy certificate, change certificate, whatever. And there are other specifications. And the demonstrator implements that on a public blockchain using public infrastructure, open APIs, open source tools, open source libraries, specification, and standards. So I was able to do that in a week because I was tapping into an ecosystem that's existing, and that is the art world. And I'm bridging from a set of open specification that can be, you can choose any ecosystem. You just need to place those layers, right? And then I'm going into the sensor models. And I still have, I think, 1 minute buffer to describe metadata a little bit. It's just JSON files describing the elements. The left is the contract. And the interesting part is it has interfaces as a description. And the interface point to the different specification. So if somebody reads the JSON automatically, he sees TZIP 16 and knows how to interpret what's coming. So and then it goes into the next layer, like an onion. And the next layer is then the next JSON file that describes the metadata of the token. And there, we are still in the world of NFTs. We are referencing to the data object. And you will see, and you can go through that in the demo, but there's a part here where you have the format, name of the dataset, size of the dataset, URL of the dataset, MIME type of the dataset. So where am I referencing to? FMUs have MIME types. OpenX do not have. So now I'm asking for the creation of MIME types for OpenX, because that enables us to link those elements together, right? And this is actually how it's done, and you can read up on it. If you want to make a photograph of the URL, you can go there, and everything is explained. And I would invite you to work with me on that and demonstrate the tokenization of every simulation data set that we have as a baseline to create open data markets for the exchange of simulation data with the goal of a virtual proof of validation. Thank you.
Questions? Yeah. Thank you very much for the very interesting work. Congratulations on that. Questions? have one question.
Yeah.
It's not related to the last part, which is very interesting. When you refer to the example of the UN R157, you had a block that was referring to quality checks and referring to CI.
Yeah. Where is it?
Could you maybe just say a couple of words about that one? How do you do the checks, this quality check? Okay,
so one very simple check is that open scenario is an XML, and XML comes with a schema. And you can use XML lint to check if you complied with the schema. So that's the first and most simple check. And then there are certain companies that also contributed to the standard that said, I think I will make a library that checks and if the standard is correct, and I'm deriving that library from the UML model. And then I asked them, what do you think about making that open source and create a little plugin so that I can put it here into the pipeline so people will see that you have the know-how to do those checks. And it's another company. And what I'm hoping to is that there are others that will come as well, and I integrate a whole more checks. So we create this network of trust of people and companies that check something and is giving you the confidence in using it.
Right. Well, very interesting. So what's very interesting for me is the usage of community or open source community to do certain type of joint work. So congratulations on that, and thank you very much for your talk.
Thanks.